So welcome to this pre-recording of lecture 40 of a course on Introduction to Symbolic Computation. This is one of our last lectures, in some sense the last lecture before the review. And the topic is parallel computing, mainly because all computers are parallel computers. Also, we have covered in the previous lecture Julia as an alternative programming language for working with symbolic computation. In the slides here, I want to make some definitions clear. How parallel symbolic computation can happen. And then in the second part, I will illustrate how Julia provides tools for multithreading. So there is some kind of disjunction in the sense that my examples will all be numerical. But the main goal of this lecture is to indicate how multithreading works at quite a high level in a language such as Julia. So what is parallel computing? So we have three types, roughly. So parallel computers can consist of multiple computers connected through an internet. That is called distributed memory parallel computing. This is not the kind of parallel computing that we consider in this lecture. What we consider is multithreading, also more explicitly called shared memory parallel computing. So processors, modern processors, consist of multiple cores, and each multiple core can handle multiple threads. So all threads share the same memory, which is not the case with distributed memory. Then the third type of parallel processing is the acceleration with graphics processing units, or with specific type of processors. So one can consider FGPAs or tensor processing units. So all three types of parallel computing are possible within Julia. We focus here on the multi-threading, the second type of parallel computing. Now, does it work? Well, there are two things one need to consider when evaluating parallel programs. The first type is that one measures the time, and typically this is the elapsed wall clock time. Speed up is typically measured the time of serial time over parallel time, or you consider the time for two threads over four threads. Given that the time for four threads will be smaller than the time for two threads, which might not be the case, the speed up will always be larger than one. That's what we hope. So this is one measure to evaluate parallel programs. The other measure, and if we talk about performance, then one typically talks about the number of floating point operations per second. So this is not necessarily in parallel computing, but it's more related to performance, and in particular high performance. I will illustrate this in a Jupyter notebook, how the peak floating point operation can be computed within Julia. Okay, so parallel symbolic computation is at first not obvious, given that we are manipulating expressions, which is very similar on how we would compute by hand. and we only have two hands. How can we speed that up? Now, expressions that we compute are of two main types. There are polynomials or there are power series. And one can look at a polynomial as defined simplistically. Polynomial in one variable of degree d has d plus 1 coefficients. And in numerical analysis, the sequel course that follows this course, we will see that you can determine uniquely a polynomial by d plus 1 function values. Why is this an interesting view? Well, the evaluation of expressions can happen independently and therefore can happen in parallel. So computing a polynomial of degree d in principle can be done d times faster. One can do something similar with power series. With power series, one can interpolate also and reconstruct the terms in the series via the fast Fourier transform. So this is kind of in a nutshell how we can do parallel symbolic computation, where we view our expressions as black boxes to evaluate. So that's one perspective. One also talks sometimes about computer algebra by values, where one stores a polynomial not necessarily as its coefficient vector, but by the function values evaluated with respect to then certain basis. Okay, so that's the high level perspective. How do you actually now do it? I mentioned earlier that Julia is targeted for scientific computing. There is a linear algebra module built in, so it's very suitable for parallel linear algebra. But there is a stumbling block. We do everything in a Jupyter notebook, so we must set an environment variable for doing the multithreading by declaring how many threads that we want to use. So with multithreading, one is limited by the capability of the processor. Here I'm doing this on a fast Windows laptop, and I can go up to 16 threads. So on your end, you may have to set this Julia environment variable to something less or perhaps something more. Now, as I will illustrate, doing parallel computing has several issues. So the first thing that you have to consider is that your problems must be large enough. Otherwise, you won't see the difference. As far as Julia goes, whenever you execute, so Julia is a programming language which you may often confuse with a scripting language, in the sense that the compilation and the linking is hidden from you, the high-level programmer. So when you run things the first time, the code gets compiled, and one should not include this compilation time when one considers the speed up. So problems need to be large enough and also be aware of the overhead incurred by the compilation. The just-in-time compilation of Julia. So I mentioned function evaluation. Numerical integration is a topic that we considered with the vectorization. So in here, what we do is that we consider the integration problem as an evaluation of the integrand. So we're going to evaluate the integrand multiple times. So in doing parallel computation, one must also carefully select the algorithms and the problems. So the problems must be important and big enough to consider for parallel computing. The algorithms that are running on them also need to provide sufficiently many parallelism. And numerical integration via the Monte Carlo simulations is an example of a pleasingly parallel computation. In a nutshell, it's throwing darts. So I have this unit disk there, and we throw darts in this circle. Some of them may end outside the circle, and we count as a success those darts that end up in the first quadrant. So we restrict ourselves to a square, the unit square, taking samples uniformly distributed in the intervals 0, 1. And we count this as a success if the distance to the origin is less than or equal to 1. This is a very naive method to integrate, but it's a method that works very well in parallel. And as a matter of fact, for high dimensional integrals, it's actually the only suitable method to estimate the values of integrals. So I will now switch to a Jupyter notebook, swap out the slides for what I have prepared. So I will run this Jupyter notebook just by scrolling through, first indicating the main step, what I did. So I defined a new kernel. So let's see if it's here visible even. No, so it's visible here. So I have my first kernel, which I installed for 16 threads. So this is done on a Windows laptop, and I'm presuming that this will also work on Macs. Alternatively, on Linux and on Macs, you can set an environment variable. The environment variable that you set for, as indicated here, what you set for the installing of the kernel. So I'm backtracking here. So these instructions need to be executed preferably in the Jupyter, in the Julia command terminal before you launch the notebook. So we define a new kernel that sets that environment variable. And then you can check whether it works. If you select that kernel, you can ask for the number of threads. If it didn't work, or by default in a normal Julia kernel, you will see that the number of threads equals 1. Okay, so that's the first important setup to make it all work. Let us then consider the parallel matrix multiplication. So I should have emphasized that the matrix multiplication is one of the major cornerstone operations. In the linear algebra lectures, I emphasized on the matrix factorizations, and one can view these matrix factorizations are leading into matrix multiplications. So if you can do the matrix multiplication fast, then you can do a lot of problems in scientific computing very fast. And parallel computing is easy if it is already predefined, precompiled in software libraries. So when we were running NumPy, and also when we did most likely numerical computations with matrices in SageMath, we most likely were already running the optimized basic linear algebra subroutines, which is used here. So I'm using the linear algebra module of Julia, which is built in. If once you have installed Julia, you can immediately start solving linear systems. I do this here with a matrix of dimension 8000. I will justify this, why 8000 is a good number. I don't really want to see those numbers, so there's a way to suppress the output when you run code in a Julia cell, in a Julia code cell. You use the semicolon. With the basic linear algebra subroutines, I can set the number of threads. And then here you see the first multiplication, and it is timed. The exclamation point indicates that the result will be written in the first argument. So it will be, so normally functions return something. Here this function indeed returns something. The matrix shows the matrix, but we have already allocated space inside the matrix by these random matrices. Nevertheless, you see the result of the computation, and you see that there is an overhead of the compilation time that occurred. So this computation took 10 seconds. We used millions of allocations, and we used that much storage. So the size of the matrix also depends on your available internal memory. Some problems are compute bound, which means that they depend on the speed of the processor. Other problems are memory bound. They depend on the speed of your memory. For the matrix multiplication, which is typically cubic in the dimension, which is already very highly compute intensive, there the problem is compute bound. All right. So you see, when I do this again, I get rid of the 4% overhead. So it drops below the 10 seconds. And you see there was no more compilation time anymore. So let me double the number of threads. So if I would run this, I would need to wait 10 seconds. So for the interest of speeding up this pre-recording, I'm not doing this. And then you see that if I double the number of threads, the time drops to 6.4. So from 6.9, almost 10 seconds, it drops to 6 seconds. So there is a noticeable gain. It's not twice as fast, but it is considerable. Okay, so that's the conclusion. Now, how do you justify your number 8000? So 8000 is already quite a big matrix. Well, there is another built-in. I mentioned performance earlier on when I showed the slides. There is the built-in peak flops, which will execute also one of the basic linear algebra routines, and that might be also the Gaussian elimination on matrices using the double precision version. So if I pick 8000, then I get a higher number than when I pick 4000, which is not large enough. But then there is this two large problems, so 16,000 also had a smaller peak floating point operation per second. So the flops indicates the floating point operations per second, and that is a measure for the performance of this computer. So this 2 to the power 11, so this is a 2 with 11 zeros added to it. So to read this number and to interpret this number correctly, so with 6 zeros we have a million, with 9 zeros we have a billion. If we would have had 12 zeros, we would have had a trillion. So we are not there yet, but still 200 billion floating point operations per second is very impressive. So this to indicate the availability of the basic linear algebra subroutines, and this is directly available in Julia. You don't need to install anything. So the Python user will install the NumPy library. So in a way, the performance that one gets is from the pre-compiled libraries. That is both in Julia and in Python. Okay, so one last topic that I want to consider is the parallel numerical integration. And here I consider a customized random number generator. So just to indicate that what makes Julia also fast is that the user can specify the types of the functions. So in the previous lecture, I was emphasizing, or it was emphasized in the explanation of the logo, when coded well. So here, the random number generator is not calling any of the libraries which would have an overhead, and it's actually specifically compiled for the 64-bit integers. So this works well for the type of parallel computation that I want to do. The Monte Carlo method looked like a very naive method, but to have a very good random number generator, there are a lot more things that need to get done. So one does not want that every processor generates the same sequence of random numbers. So I want to emphasize that this is just a toy example here. This is not a numerical computation that we are running for hours. Our runtimes are seconds. That's why I get away with a very basic random number generator. And this fits also in the context of a first introduction to Julia, where the documentation strings come before the function prototype, before the function implementation. I want to indicate that here every function is customized with the thread idea. So I'm using the threads, and when this function will run, this function will be executed by as many threads as I have available in my environment here. Now, the random number generator takes in an initial number and does a linear combination with this. So every random number generation has a seed, and the seed for the random number generator is based on the thread idea. So it is based on the identification number of the thread. In this way, I will be certain that every thread will generate a different sequence of random numbers. So the first instruction is very important. So we can write very short code, but every instruction actually matters. So then we run this loop and we generate two numbers, so they are numbers in 0, 1. There are 36, so we do the modulo with 31. We divide, so these are become essentially then floating point numbers. And we count as a success all the numbers that for the squared distance are less than 1. So they are in the unit disk in the first quadrant. That's why this function multiplies by 4. So we have the ratio of the successes over the total number of samples that gets returned. Okay, so we have the number of threads. So very important in shared memory is that all threads have access to the entire memory location. So there are many things that can go wrong with threads that write in the same memory location. Here we will prevent this by allocating a vector of zeros. So the first thread writes to the first element, the second thread writes to the second element. So the memory space, which is here, so this is a very computationally intensive calculation. So the data is just a vector of 16 elements that will hold the results. I can compute the average with a simple formula, but I have used the statistics module. And now comes the other construction. We can define a parallel for loop. So this parallel for loop will actually map the function estimate pi to the threads. So it is a loop, but the loop is a parallel loop, so it's executed instantaneously. So all 16 threads, if I run this with 16 threads, will execute at the same time. And here you see where the parallelism comes in. In order to have the same amount of samples, the total number of samples is divided by the number of threads. So I have 10 billion simulations that will be done. If I work with 16 threads, then that total number is divided by 16. Okay, so I start the time, and the calculation actually also includes here the computation of the mean, which is a sequential operation. So I could have swapped these two statements, but perhaps in more better computation, we are interested in the total time, in the total elapsed time, which also includes this sequential time, which is essentially just adding up these numbers and divided by 16. Okay, so this goes with 16 threads, runs with a little bit over 6 seconds when I did this. And let me now redo this. So by the way, in explaining Julia, so the print statements work with interpolation. So there is this dollar sign, which, so we have the variables in Julia that are interpolated in the strings. Okay, let us redo this calculation now for 8 threads. So I copy and paste the execution blocks. Estimating, so I did not redo the initialization, which is fine because the functions they just assign. So the initialization to zeros did not need to re-happen again. You see the difference with the number of threads, and you also see the slice when I compute the mean. So that means that I have still about the same accuracy, so the accuracy is not very high. The time actually went up from 6.1 to 9.2. So in doubling the number of threads, going from 8 to 16, I have a speed up of 1.5, which is not that bad. So as an exercise, I would suggest that you play with this, adjust this for your own computer. And here I tried to indicate how high level parallel computing works. It works well for within Julia. So we had observable and realistic speedups, provided also here that we choose our problems large enough. So this is for 10 billion simulations. It would not work if you are more frugal with your Monte Carlo simulations. Also, one needs to take a different view on the problem of numerical integration, at least when one wants to do this in a very straightforward manner with Monte Carlo. Okay, I hope this lecture was interesting, and I stop the recording now.